Welcome to Lecture 22 of Electrical Engineering 525. This is just a quick lecture on the use of the Friis transmission formula to calculate the available power received at a receiving antenna based on the gains of the receiving and transmitting antennas and the power transmitted and the distance between the antennas. What we're going to do in the video is to cover, to actually work out problem 4.4-13, which says calculate the received power in watts for the DBS system of example 4-4 using equation 433. We're going to start off by talking about what example 4-4 is, and you can see that here in this second paragraph, and actually that refers, it says this example completes the satellite TV receiver case study of example 4-3, so actually we need to begin with example 4-3 to understand what's going on. Once we understand example 4-3 and then understand example 4-4, the actual calculation for this problem is relatively straightforward and quick. So this will be a quick lecture. So let's start with example 4-3, and you can read along here. Reception of high quality television channels at home with an inexpensive small terminal is possible as the result of many years of technology development, including new antenna designs. DirecTV transmits from 12.2 to 12.7 gigahertz with 120 watts of power and an EIRP, as you will find in your reading in chapter 4. EIRP is effective isotropically radiated power. So EIRP of 55 dBW in each 24 megahertz transponder that handles 5 compressed digital video channels. The receiver uses a 67K noise temperature, low noise, block down converter, and when combined with antenna noise gives a system noise temperature of 125K. Here we do the noise analysis for this satellite link, and we'll use the result in the link calculation of example 4-4. So you can look in your book if you're interested in seeing the details of example 4-3. But then the results from example 4-3 are used in 4-4, and that's what this particular problem, problem 4.4-13, is referring to. So let's look at example 4-4. It says, this example completes the satellite TV receiver case study of example 4-3, in which the noise power was calculated. Each 24 megahertz transponder handles several compressed digital video channels and transmits 120 watts of power from the satellite. The EIRP is stated to be 55 dBW. The receiving system uses a 0.46 meter, 18-inch, diameter offset-fed reflector antenna. Here we find the received signal power using the following link parameter values. And for our problem, in our example here, you are to use these same values. So the frequency is 12.45 gigahertz, which is right in the middle of that 12.2 to 12.7 gigahertz band that is mentioned in example 4-3. The transmitted power in dBW is, and what that dBW means is that if the transmitted power is expressed in watts, and then you take 10 times the log of that, this is the number that you'll get, 20.8. And you can check that the power, the transmitted power is 120 watts. So that's already expressed in terms of watts. So just take 10 log base 10 of 120, and you will get 20.8. So that's what dBW means. So the transmitted power is 20.8 dBW. The gain of the transmitting antenna in dB is equal to the effective isotropically radiated power in dBW minus the transmitted power in dBW, and that's equal to 55 minus 20.8, or 34.2 dB. And that end result is all you really need. You don't need to really know the details of how it was calculated. You just need to know that GT, the gain of the transmitting antenna in dB, is 34.2 dB. R is equal to 38,000 kilometers, which you're told is a typical slant path length. And finally, GR is equal to 34 dB. And actually, in the example 4-4 in your book, you'll see more details about how that 34 dB was calculated. But again, you don't really need to know those details. You just need to know the final value. So now, getting to the problem, which is to calculate the received power in watts for this system. Here is the famous Friis transmission formula that you should use for this kind of problem. And it says that PR is equal to PT times GT GR lambda squared over 4 pi R quantity squared, where PR is the available received power, PT is the transmitted power, GT is the gain of the transmitting antenna, GR is the gain of the receiving antenna, and R is the distance between the antennas. And as you might suspect from the fact that this formula is so simple, there are a number of assumptions upon which it is based, but still it is a useful formula, despite the fact that there are many assumptions built into the formula. So what we want to do for the lesson is to actually calculate this for the values given, and then for test 22, for problem 1 of test 22, we will make a slight change in this problem, and you will see what effect that has. So now to proceed with this problem, you know that, again, GT in dB is 34.2 dB. And likewise, GR is 34 dB. I left off dB there, but it should be there. So since those are the values of GT and GR in dB, then to get GT and GR, we note that 10 log GT is equal to 34.2 and 10 log GR is 34. And so if we do those calculations, we will see that the gain GT is 2,630.27 and GR is 2,511.89. So now we have two of the parameters needed here in the Friis transmission formula, and the next thing we'll calculate is lambda. Lambda, we know from previous work in this course, is equal to c, the speed of light, divided by the frequency. And the frequency is 12.45 gigahertz, and c is 3 times 10 to the 8th meters per second. So when we do this calculation, we'll get 2.4096 centimeters, or 2.4096 times 10 to the minus 2 meters. So now we're ready to go ahead and substitute everything into the formula. And I will caution you about a couple of things. Do notice again in the Friis transmission formula that it's not 4 pi r squared in the bottom, but the quantity 4 pi r, all of that is squared. So really it's 16 pi squared r squared in the bottom. So don't make a mistake on that. And then another thing to caution you about is that remember that R is 38,000 kilometers. So you have 38,000 here, and then 10 to the 10 to the third power, because it's 10 to the third for the kilo part of kilometer. So you need to include that as well. And then you will have meters squared coming out and meters squared up here. So those will cancel, and then you'll be left with just this unit, watts, which is what we want for this problem. And so if you turn the crank on all of this using the values that we've calculated, you'll come up with this 2.019 times 10 to the minus 12 watts, this very small value for the received power, which is typical in this kind of problem where the antennas are so far apart. So that's the way that we use the Friis transmission formula. And now let's look at problem 1 for test 22. It says in this same problem, if R is increased to 50,000 kilometers, what must the gain of the receiving antenna become in dB if everything else is to be held constant? So if we want to still have that same received power, and if we want to have the same transmitting antenna and the same transmitted power, if all of that is going to stay the same, but the receiving antenna is moved to a distance, instead of 38,000 kilometers away, it's 50,000 kilometers away, what must we do to the gain of the receiving antenna? What must it become in order for the received power to remain the same? And so, and the answer is given here in dB, and the four choices are A, 44.74 dB, B, 58.86 dB, C, 36.38 dB, and finally D, 35.19 dB. So that's all for lecture 22. Good luck.